Let's imagine a reaction that is in equilibrium. So A plus B, they can react to form C plus D, or you could go the other way around. C plus D could react to form A plus B. And we assume that they've all been hanging around long enough for this to be in equilibrium, so that the reaction that goes from A plus B to C plus D, it's happening at the same rate as the reaction from C plus D to A plus B. Now what we're going to do is imagine what would happen if we disturb this equilibrium. And let's say we disturb this equilibrium by taking some C and D out of, let's say this was a solution of some kind. So I just one time reduced the concentration of C and D. Well, that disturbance, first of all, is going to throw us out of equilibrium, because now the reaction that goes from C plus D to A plus B isn't going to be able to happen as often, because I just took C and D out. They're not going to bump into each other enough to now form A and B at the same rate. So if you think about the net direction until we hit a new equilibrium, this is going to happen less, and this initially is going to be happening at the same amount. So you're going to have a net direction until we hit equilibrium again that goes from A plus B to C plus D. And then if you wait long enough, you're going to hit back at an equilibrium. Now let's think about what just happened. We disturbed the equilibrium by taking C and D out. Until we hit our new equilibrium, we have more of the reaction going from A plus B to C plus D on a net basis. And so it's relieving it. It's relieving the fact that we took some C plus D out. And it's going to reestablish a new equilibrium. If we took A plus B out, or A and B out, or even just one of them, A or B out, then you would have the opposite happen. But either way, if you disturb it, the system shifts to relieve the disturbance and reestablish equilibrium. Now this principle, you might imagine, because it's been sitting here the whole time, is Le Châtelier's principle that describes that. And it's not just by disturbing it by changing, say, concentrations of reactants or products. You could be changing other things. So for example, let's imagine the reversible reaction. Let's say A plus B, and let's say these are all gases. So A plus B can react to form C, or C could react to, I guess you could imagine, break up into A plus B. And let's imagine that these are all gases. So let's assume that's happening in a container of a certain size. And let's say that I were to shrink the volume of that container. What do you think is going to happen in that situation? Well, if I shrink the volume of that container, then you have a situation where A and B are going to bump into each other more. They're going to collide into each other more. And so you're going to have a net direction going that one. You'll still have some C reacting to break up into A and B, but you're going to have more A and B reacting, bumping into each other, colliding each other to form C until we hit a new equilibrium. And notice what is happening there. When A plus B reacts to form C, it decreases the number of particles in the container, and it decreases the pressure. And so eventually, you're going to hit a new equilibrium. But when you disturb that equilibrium by changing the volume, the system shifted to relieve that disturbance. In that case, the disturbance was an increase in pressure, and it reestablished the equilibrium. Let's imagine another reaction. Let's imagine A plus B. And let's say this is an endothermic reaction. So I'm going to treat energy really as a reactant here, just to make it clear that this is an endothermic reaction. That could form C plus D, or you could have C plus D react to form A plus B plus energy. So the reaction that starts with C plus D and forms A plus B in energy, well, that's going to be exothermic. So let's imagine what would happen here, and let's imagine it's at equilibrium, but then we disturb that equilibrium. What happens if we disturb that equilibrium by adding more energy over here? Well, if I add more energy, it's going to be easier for this endothermic reaction to occur, and so it's going to disturb the equilibrium in that direction right over there. And so you're going to have that energy really get used up to form more C and D. You could imagine the other way. What happens if I were to take energy away? Well, you need energy for A and B to react to form C plus D. So if you were to take energy away, then the reaction that starts with A and B is going to happen less. And so you're going to have a net direction with C plus D reacting to form A plus B until you hit a new equilibrium. But the important thing to realize here is in every situation, whether we're disturbing the equilibrium by changing concentration, by changing volume and therefore changing pressure, or you're adding or taking away energy, which you could do in the form of changing the temperature, the system shifts to relieve that disturbance and reestablish a new equilibrium, which once again is Le Chatelier's principle.